We've seen how to handle our indeterminate beams, so now we need to deal with our indeterminate trusses. We are still going to use force method. So this truss up above, which again is a pretty common bridge situation, we can idealize pretty simply with something like this. Pin and 2 rollers at the supports along the length. And if we were to check the determinacy on this, we would find N as the number of joints, 1, 2, 3, 4, 5. R is the number of external reactions, 1, 2, 3, 4, plus the number of members, 1, 2, 3, 4, 5, 6, 7. So we get R compared to 2N. 11 is greater than 10. We are 1 degree indeterminate. And because we're seeing our external reactions as greater than 3, we are going to call this externally indeterminate. And just like our beams, where we took off a redundant reaction and put a unit load back in its place, that's exactly how we're going to deal with the indeterminacy for that type of truss. Externally indeterminate, we cannot use equilibrium to find external reactions. Just like we saw with the beams, we're going to have to take off a support, put a unit load back in its place, calculate some deflection, and we'll be able to find that additional reaction or more. That's more degrees indeterminate. So if we look at this next truss, which again is another fairly common looking truss, we can do the same thing. Check determinacy. 1, 2, 3, 4, 7, 8. I'm going to assume this isn't connected, although it doesn't matter if it is. We would have N as 9, and then we'd have more members, so the math will be the same at the end of the day in terms of degrees of indeterminacy. We have 3 external reactions, a roller and a pin, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 members. So R compared to 2N, 17 is greater than 16. We're still 1 degree indeterminate, but now we're in the conundrum where our external reactions equals 3, and if I try to take one of these off, I'm going to end up with an unstable structure. If I try to take the roller off, it's just going to be rotating rigidly about the pin. If I change the pin to a roller, it's going to be like it's on a skateboard on the side and just rigidly roll away. So this is what we call internally indeterminate. And what that means is, instead of where we have the external where I can drop this number to a 3 by taking off a support and getting that to equal 10, and thus having 10 equal to 10 for being determinate, I'm going to have to adjust the other number that's part of my R, which is my number of members. So I'm going to want to drop that down to 13 to make this 16 equal to 16. So when it's internally indeterminate, meaning my external reactions are equal to 3, I'm going to have to remove a member, put a unit force back in its place, and calculate some deflections. So the overall steps are the same. The only change is what I'm going to take off. And where we might run into some issues, if it's internally indeterminate, we can use equilibrium to find the reactions. But if we jump in and start trying to do method of joints or method of sections, we're going to have a really bad time because we're always going to have just one too many unknowns. So we're not going to be able to find all the internal forces in our truss, which is problematic because then we can't calculate deflection if we can't find little n and big N because we have an indeterminate truss. So that's where we're at. We've got 2 options. This first one, if our external reactions are more than 3, we're going to treat it exactly like we did the beams. If our external reactions are equal to 3, we are now internally indeterminate, and we're going to have to handle this a little bit differently, but still the same general steps.